Okay, there's a little silence, so I guess you're ready. So I want to kind of do the last piece of the legged robots section, if you will, and talk about what happens differently when you get up to a more complicated robot, right? So we've given you a handful of tools now, I think fairly elegant tools for thinking about legged robots and thinking about possibly summarizing discontinuous collision events with hybrid models. We've given you trajectory optimization and now stabilization and even Lyapunov analysis for these things. Shown how to do them for trajectories, for limit cycles. And I've given you a series of models, maybe starting from the rimless wheel to the compass gate to the kneed compass gate, and sort of implied there's a natural progression as you just add more and more links, right? We have the basic machinery for how to do that. But the thing I don't like about this, and the thing I hope to address in the lecture today, is that the picture I've given so far sort of makes it seem like going from here, up to a full humanoid that's doing backflips or something. It just gets harder and harder and harder after you add every link you add. Okay. In fact, that seems like sort of inconsistent with the fact that we've seen for years robots, full complicated humanoids walking around and doing pretty wonderful things, making non-trivial plans on the fly, avoiding pedestrians, for instance, right? So if they're solving just really complicated hybrid nonlinear optimization problems, it seems like somehow something's missing. There's a gap between this progression of what seems like harder and harder problems that are susceptible to local minima and other things versus these kind of robust results we've seen from the humanoids. Okay, so I want to try to close that gap today and tell you some things actually get easier when you have more degrees of freedom. Okay, some simplifications become useful once you have enough degrees of freedom to sort of abstract away the details of your joints. And then some of that is useful all the way back from this is maybe, you might not like how dynamic that is, that's not a backflip yet, okay, but the lessons from these humanoids are actually general purpose and can be used in trajectory optimization and all these other things. Okay, so one of the key ideas here for today is the notion of centroidal dynamics. Okay, so ironically, as the robot gets more complicated, the simple models start working better again. Okay, you can abstract away the details of your links and think of yourself as a centroidal blob moving through the world. Okay, so to put that in context, maybe think about just something you might have more intuition about. Think about if you're an astronaut in microgravity. Okay, maybe you have some, at least somewhat intuition about what it would be like to be floating in microgravity, right? You know that your center of mass is if unperturbed, your center of mass isn't going to move. You could do all you want, your center of mass isn't going to move. If you were to push off a wall, you could cause a change in your center of mass, but only from the forces that you're exerting, right? Your angular momentum is conserved. These are the intuitions, right? It doesn't really matter what you're doing with all your links. That is always true. I mean, this is a complicated humanoid, right? But the center of mass dynamics are very simple, right? When you add gravity, it's maybe, it's still simple. It happens to be that you're pulling into the ground, okay? But actually, just the abstraction of what your center of mass must be doing seems a little bit more clear in my head when I think about an astronaut in space moving around, okay? So it turns out that's the secret, is that even when the robot has many links, the center of mass dynamics are still simple. And if you look at the simple robots, right, actually you can't, the center of mass dynamics in some sense are harder in these models. They have to go, the center of mass might have to like go through a parabolic arc here, or there's other constraints on what the center of mass can do. But if I have enough links, then actually I can command the center of mass to do whatever I want. I can move it up and down in all the directions, and I can abstract away the details of my legs and think about the details of my center of mass. Okay, so that's the story. I'll leave him up there, he's smiling. Right, let's just think about, the basic concept there is if I've got a humanoid, maybe I'm an astronaut floating in space. That's a really bad astronaut, okay? But all that matters is if I have the x, if I'm doing it in the plane, let's say I've got x and z. I'll do most of the things in the sagittal plane, but certainly it could be x, y, and z. If I'm applying a force, if I grabbed something in the spaceship, let's say, and I'm applying a force here, or I'm pushing off this, and so I'm getting a reaction force that's like this, some sort of force, then that's going to have a simple effect on the acceleration of my center of mass. Okay, and we saw that before. We saw, it's actually not so far from what we saw in the quadrotor dynamics, right? I just have a couple of forces being applied to a body, but I want to start with this abstraction. Okay, so let's just say I've got a body B and a force being applied, okay, at some position. Let me write it a little bit differently than I wrote up there, and we'll compare the differences just to make sure it's clear. So if I have a body B here, I'm going to say that mx double dot is going to be the sum of all the forces in the x component of the forces. In our slightly heavy but hopefully clear notation, I would say that this is a force written in the world, expressed in the world frame, and then this is the x component. And I can have many forces. This is one that's going to be applied to body B at point BI. Okay, but the main thing is I just take the x component of all the forces that are being applied. I could have multiple forces. I could have force B1, force B2, and the x component of all those forces is the only thing that affects the x component of this, right? Even if I add gravity, it's not any harder. I mean, it's not so good for him in that position, but right, I just got negative mg plus all of the z components of those forces. And even if I have an orientation of this guy in space, right, just like the quadrotor, it's actually simple dynamics, which is just, it's a cross product. I have the torque is going to be the cross product of the force times the position to that force, okay? More than understanding the physics, I want you to understand the implications of how these enter the equations, okay? So this is a position of the point BI relative to body coordinates B expressed in W. It's funny because when I teach the manipulation class, I try to go carefully through the notation because you just need it all the time everywhere. In underactuate, I got like this far without needing it, and then today I was like, oh, I kind of need it for the humanoid case, okay? So there's a lot of write-up about the notation if you want it, but hopefully you can run with me and accept that there's a couple superscripts and stuff like this in order to just keep the frames clear, basically, so I know that I'm applying these in the same coordinate systems. Okay, so this is almost the same dynamics as that, but it looks a little different just because of the frames exactly, is that I said that the forces coming in here, I express them in a world coordinates, in this world coordinates. Here I called U1 and U2, and I put them in body coordinates. So there's a sine and a cosine affecting x double dot and y double dot. In this version, the sine and cosine are hiding in the position because I've taken the body and I've put it into world coordinates. So I had to use a sine and a cosine here. But it's the same dynamics, it's just I've written it in a different coordinate system. The reason that this is my preference for today is because, first of all, the positions let's say my astronaut might grab in space are actually bound to the world, maybe more than they're bound to the astronaut, right? So the positions might naturally live in the world coordinates. And if they're fixed in the world coordinates, then those sines and cosines don't even appear. Okay? And moreover, if you look at these equations now, even though they've got position and orientation, if this is fixed in the world coordinates, then, sorry, my phone's ringing. Okay, then actually the dynamics are linear, or affine in this case. They're actually affine in the forces. So if I think of forces as a control input, then I actually have a linear system of equations, or affine systems of equations. I could do LQR on this. I could do linear model predictive control on this if I took the forces as my control input, and I just wanted to control the motion of the center of mass. You guys don't look happy with that one. Let's say then I basically have MQ double dot equals U. I have a plus some offset because of this. Okay, but the equations are almost linear in U. I guess I've got a multiplier there. So it looks like a second order system that would be linear in U if I took the forces as input. Okay, so that is actually a second piece of the reason why humanoids can work fairly well, is that if you write the dynamics in this center of mass coordinates, then the dynamics are actually easy as a result of thinking about through the contact forces. Okay, so for me, the problem of walking is a little bit like the problem of like a quad rotor, or this problem of an astronaut or something like this, right? I mean, think about, just to make that analogy kind of strange, but let's say, so right now I've got a, I'm used to a quadrotor where the propellers are moving around with my quadrotor, okay? But what if I had, it sort of seems sort of strange, but what if I had body fixed propellers, okay? Or sorry, world fixed propellers. I've got a series of propellers locked around in the world that I can turn on or turn off. This is me grabbing a handhold and pushing, for instance, and I'm trying to move my body B through this space. And maybe there's some rules. I can only turn on the things that I can reach, okay? So maybe I only get to turn on the ones that are close enough to the body. And my problem now is if I want to, let's say, move my astronaut through the International Space Station, I've got to pick the propellers to turn on or the hands to grab in order to produce the forces, in order to move this through. So the game becomes actually, the dynamics in some sense become easier, they become linear, but there's a discrete decision to make about when do I grab a particular handhold, when do I put my foot on a particular foothold, okay? And it moves some of the complexity from the continuous nonlinear dynamics like we see in the simple walkers to a more discrete but linear plus linear dynamics that we see in the humanoids. To continue the questionable drawings, let me draw my little humanoid here, okay? So if I've got a humanoid walking, okay, it's the same picture, right? So if I had a body B here, and it's got his X, Z position, that's why I used Z, right? And I've got force 1, force 2, for instance, force 3, force 4, I should use the superscript, 2. Okay, it's the same, especially if the legs are massless, for instance, then it's exactly the same picture, right? I've just got to, I get to put my foot somewhere, and I'm just trying to push and move around my body. And then the leap you want to make, okay, is that even if the legs have mass, the dynamics are still identical if I change this from being some fixed point on the body and now treat it as the center of mass of the multi-link system, right? The multi-link system can always be abstracted into a single, center of mass that's moving through space. It might move relative to the torso, okay, but the dynamics are simple functions of those forces and gravity. Yes? Same thing is going to be true for angular momentum. The center of mass is a point. It's not even a body fixed point anymore. So it doesn't have a momentum, okay, but you can talk about the natural extension of thinking about the angular momentum of many link system would be just to say, what's the angular momentum of this whole robot about the center of mass? That's the centroidal momentum, okay? So the centroidal dynamics are the center of mass plus the angular momentum about center of mass. That's the dynamics of those. So if you can choose, potential footsteps and potential, if you can choose your potential footsteps and the corresponding ground reaction forces, then you can plan a center of mass and angular momentum trajectory without worrying exactly how you got there, right? As long as I know that I could find a set of joint coordinates that would get me there, right? For any possible foot positions that are kind of here relative to my body, the details I can figure out later. So that is a very nice way to sort of separate the problem and come up with a simple planning problem for the center of mass with some discrete decisions. And then later we figure out the nonlinear kinematics and everything like that. So this, back when I was thinking about this a lot, I was trying to sort of tell the story, and I actually asked my artist friend to just make a little video to help me tell this story. And so this was the picture. I said, okay, imagine you're doing parkour. What you should be doing first is thinking about, your contact points, right? And then afterwards, and you actually are plotting. It was hard to draw. We actually tried a bunch of illustrations to make it draw like the contact forces and the angular momentum and stuff. It was just too messy. But imagine you're moving through space, even if you're doing parkour. If you separate the problem and you first make a plan of just, I'm going to push here, I'm going to push here, I'm going to get a contact force like this, that's going to let my center of mass do this. Everything else is a detail you can fill in later, to some extent. The only thing you lose doing that is if something becomes unreachable, let's say because of a joint limit, or you can't produce this force and this force simultaneously because of like some torque limits that are at the joint level, then you could miss that, okay? But the general, apart from those some joint-specific limitations, this is all you need to know. It's not an approximation. That's all you need to know about your center of mass dynamics. Yeah, please. So the short answer is yes. It turns out there's one more simplification, which is the zero moment point simplification. I know. So I was thinking earlier today, well, people have already looked at ZMP on the problem set. I meant to, I normally would try to have the lecture before the problem set. It was a little bit out of order. But I'm like, oh, people are going to be already masters of zero moment point. By the time they get here, they're not going to want to hear about it. And then as we were walking here, I was talking to people, and I think that's not quite true. Maybe people do want to hear about it because they spent 2 hours on the stupid problem set and they don't know what's happening. So I can go into more or less detail about that. You guys can choose your own adventure. But yeah, so the reason that you don't see forces often in the planners explicitly is because the abstraction of zero moment point is a sufficient description of the forces. But if philosophically the answer is yes, and there's just that one detail why you don't see it, F's in the equation. Any other questions at that high level? Yeah.
I guess since your moment of inertia is a function of your state, does that muddy this relatively clean picture that we've established?
Yes, good. So when you go to execute it, then the details so it'll be a function of let's say the joint angles Q. Yeah, center of mass also will be a function of the joint angles Q, right? So there is a nonlinear dependence on Q, and that's why if we separate it out and just say I know that there's going to be a Q, but I'll solve it later. Then we ignore the dependence in the first pass. It's an approximation, but it's a pretty good one. Good question. Okay, there's one other really nice thing that even before I mentioned the zero moment point that's about this picture. So if I'm going to think about the dynamics of the center of mass and the dynamics of I'm going to mostly focus on center of mass. The angular momentum follows. It's just a sort of more notationally heavy and stuff like this, but the same concepts mostly apply. So I'll talk mostly just about maintaining your center of mass. So, we spent a lot of time talking about impacts and impact equations and discontinuities. And you also don't see that very much in the humanoid literature, okay? And there's a simple reason for why, okay? And it's, of course, it's one of the reasons why you see humanoids walk like this, right? If you keep your center of mass, actually what matters is if your center of mass acceleration, if z double dot is 0, then we'll see in the equations, it turns out that your contact force cannot be doing any work. Okay, so if I'm regulating my center of mass height to be a constant height, That's the simplest case. If my center of mass, not just it's tempting for me to make like my hip be a constant height because I can think about that a little more. But if I actually made my center of mass be a constant height, then that must mean as my foot is coming down, something else is going up, and actually zero energy is imparted in the ground. Because otherwise my center of mass wouldn't be staying at a constant height. Force would be doing some work, okay? So one of the reasons you see this, and then you can simplify it, just ignore collisions, is that effectively you're setting your foot down softly enough. Sorry, this is hard for the camera. You're setting your foot down softly enough that there's effectively no collision. So the picture of this hybrid jump kind of disappears. Okay, you lose something because impacts are good. They were stabilizing in the rimless wheel and in general are stabilizing phenomenon. Okay, and maybe you're doing a lot of energy. I won't walk backwards, right? You're actually wasting energy. This is not a particularly energy efficient way to walk. First of all, having your knees bent is tiring, right? But even slowing your foot down in order to have no impact with the ground, that's like kind of a waste of energy. Okay, but makes the equations easier. So that's good. Okay, so let's think about exactly what's happening in the equation and maybe what the zero moment point is and why that takes the forces and makes them, it's a nice summary of the forces. The ZMP is particularly potent in the case of flat ground. It actually does extend pretty nicely. But let's just think about the dynamics of my center of mass. Basically, those equations right there. In the special cases of where all of my forces are coming from the same ground, okay? Okay. The punchline, just to give it to you first, is if I'm thinking about, it turns out that I can summarize the total effect of these forces on my center of mass dynamics with a single point, which is going to be the center of pressure. In this case, it's equivalent to the zero moment point. And if you just know the location of that point, and you have this constraint that z double dot has to equal 0, which is why the magnitude doesn't matter, okay, then just knowing the location of that point relative to the location of your center of mass tells you everything about the acceleration of your center of mass in the z coordinate. So if I'm willing to stick with my z being a constant height, and I just want to know how is my center of mass going to accelerate in the x-axis, then the only thing I need to know is where is the center of pressure of that set of forces. Okay, that's a magical thing which makes all of our planning really powerful. But let's just define it. Okay, so if the center of pressure is just like you would define a center of mass, you can define a center of pressure in my slightly heavy multi-body notation here. It's going to be the x components bless you. So it's a weighted average of actually the z components of the vectors weighted by the position in x. Z here weighted by the positions in x. So it's sort of natural, right? So I want to summarize, if all of the force was here and everything was small, then I want my center of pressure to be here. okay? All the forces here, right? This is just a way to sort of interpolate and take a weighted average of those forces. Very analogous to the center of mass. If I were to say the position of this and the mass of one body times the sum of the masses, that would be the center of mass, okay? And what's amazing is that the center of mass dynamics are such a simple function of the center of pressure. So just knowing where that center of pressure in and having fixed my center of mass height tells me what the acceleration of my center of mass is. And this is the point where I thought I won't go through all the equations. They're in the notes and people have thought about it, but you can ask. You can choose your own adventure. So first, is the intuition clear? It's maybe surprising, but yes?
Isn't center of pressure always just directly under the center of mass?
No.
Okay.
No. Otherwise, that would be, you would not, when you're accelerating your center of mass, it's not. That's exactly the relationship. So when you're standing still, it is. So when you're not accelerating, it is. Okay? But as soon as you're accelerating, the center of pressure moves. It has to. That's a good way to think about it. Other questions at the conceptual level, or even at these equations level? Yeah.
Is this kind of like an inverted pendulum, more or less?
Yeah, so people sometimes call the ZMP model the linear inverted pendulum, the linearized inverted pendulum, where the height isn't moving, but otherwise it's a lot like an inverted pendulum.
Okay.
Yep. I didn't write that, but that's a common nickname for it. Good. Yeah.
Does this include like the joint given constraint?
It does not say anything about joint limits. We've explicitly said we're going to separate the joint level constraints to a post-processing step. Yeah.
Just to tie the pendulum part together, you basically have a triangle where the vertical component is equal and opposite to the weight, right? And then the hypotenuse is the total force, and the horizontal component is what accelerates you. Is that?
I think that's, so let's see if I say it back to you. Yeah, so I think the normal inverted pendulum, of course, looks like this with an angle. We're going to think about it's actually a little bit more like a mass on a table that's balancing or something like that. Okay, so you're moving this mass around on the table. The mass isn't, but you're not allowed to rotate. It's a slightly funny model. I think the statement came from just that this structure looks a lot like the pendulum equations. Yeah. But you can make a cart table sort of analogy for it.
It's like an airplane in level flight is, I think, closer.
So for those of you that are trying, to find these kind of connections, I mean, one of the things that's interesting about this is this is a non-minimum phase dynamics. Okay, as a linear system, it's an interesting linear system in the sense that in order to make my center of mass accelerate this way, sometimes I have to like go the other way first, you know. I have to move my center of pressure in the opposite direction in order to start accelerating and then go back the way I was really intending. But as long as your airplane does that too, I would be willing to concede the point. Okay, so this falls out of those equations fairly naturally. There's two ways to see it. One of them is directly from the center of pressure definition we could work with. or we can talk about the zero moment point definition. So the zero moment point definition, maybe, if I have any body B and it's experiencing a bunch of forces, wherever they may be, I can always summarize all of the forces as a single force at any point, okay, called as point A. I can summarize the total effect on a body from many forces as a single force plus moment. That's just rigid body mechanics, is that I can just, forces add in the multi-body equations, okay, and I can summarize them all from a point of force in a moment. So if you choose to put that summary in different places in space, then the force component will shift, the torque component will shift. And there is a particular place that you can pick. There's actually an entire line of possible places you could pick, okay, where the force component is non-zero, but the torque component turns out to be zero. The summary of all of these forces, where the effect of FA is the sum of BIs, okay, and the torques are zero. Though any point where the summary of all these things has zero moment required to describe it is called a zero moment point. Sort of reasonable. What's surprising maybe is that the zero moment point turns out to be, in the place where the zero moment point that's on the ground, so there's a whole line of possible zero moment points in the general case, but when the body is flat and we make the same assumptions, okay, the place that the zero moment point intersects the ground is exactly the center of pressure. All right, so those are, in all of our definitions, equivalent. I linked in the notes a paper that talks about the many definitions people have used in the literature about zero moment point and how they're slightly inconsistent. So if you see a paper that doesn't use it quite that way, go look at Goswami's paper and you can see why there's confusion in the literature, okay? But I think it's perfectly useful to think of it as a center of pressure. All right. So what level of detail do you want me to go into? Should I? That was all I was planning to say, but I can say more if there's useful things. Yeah.
Intuitively, what's the line going to look like? What is it perpendicular to?
What is it perpendicular to? I can write the line equation down. We could look at it. Let me think about it for a second.
Oh, I guess it's going to be parallel to the total force.
There are properties like if you're angular. Yeah, I don't have a general picture for you, but there are many properties associated with it. Like you wouldn't be surprised. If your center of pressure, if the zero moment point, if this reaction force, starting from the zero moment point goes through your center of pressure, then you also have no angular momentum change. There's a bunch of geometric properties like that. What does the line look like? I haven't thought about that. There probably is a geometric interpretation. I just haven't thought about it. Yeah, Frank.
Yeah, in the case where you're doing this for like a foot, for example,
Yep.
How do you want to model the contact forces? Do you idealize it as just like the heel of the toe? Do you consider distribution of forces across the foot, in which you would have to do some form of integration?
Okay, this is the great question. So Frank says, how are we going to model the different forces? Okay, let me come back to that when we do the planning, because I'll tell you what we do, and then we'll revisit why we didn't have to think hard about the contact models. Once you see the recipe that we actually execute, and it'll be missing, we'll revisit it then.
Yeah, is there, what would be the motivation of like setting up this whole concept of like 0 moment points? Like, is it more computation efficient than just doing
It's partly actually the answer to Frank's question. So the question is, what's the motivation? Part of the answer is the response to Frank's question here, which is that I don't have to do any detailed modeling of the ground reaction forces. If all I know is where the 0 moment point is on the ground, then I already know what my center mass is going to be doing. So it actually obfuscates the complexity of the ground reaction forces. It also happens to be an easy thing to measure. If you have force sensors in your feet, you can measure where your center of pressure is, okay, and you can know instantaneously where it is. It also happens to be a fairly easy thing to regulate. I can often change my 0 moment point just by like applying ankle torque, for instance. And so I can change the center of mass just with even fairly simple control, okay? But the big thing is it's exactly what you need to know about all of the forces and nothing more. Okay, yeah, go ahead.
Yeah, can the 0 moment point be outside the area of support for a foot, or does it have to be within the foot area?
Awesome question, right? So that's the place where these definitions can depart, right? So, so let me make sure I answer it carefully. And that's where all the different definitions of 0 moment point are different. Certainly the center of pressure can never leave the foot, as I've defined it, right? So it's just a weighted average. Oh, it's of the support polygon, okay? So if I put a convex hull around all of my contact points, if I'm on flat ground, then the center of pressure will be somewhere in the convex hull of my contact points, always, okay? The 0 moment point is also, since it is the center of pressure, is also inside that convex hull, okay? But when you're tipping, if you're actively tipping over your contact, then they can differ. The point where you'd have, because you have a moment, right? And so the place that you would need to have 0 moment could be outside. But as long as you are not tipping over your foot, so you have some foot flat on the ground, for instance, then the 0 moment point equals the center of pressure. Yeah, it's only when you have a moment, the center of pressure is stuck inside the support polygon and the 0 moment point is outside. And maybe because you mentioned that, so one of the interesting things is the ZMP stability criteria. Which will come up in the planning, okay? So I should say stability in quotes, since we know a lot about stability now in class. So if I have foot 1, this is now a view from above of my humanoid looking down on my big flat feet here. Okay, foot 2, and I said that this is the convex hull. This is my support polygon. Is that sort of clear? Okay, if I'm looking down, the center of pressure should always be inside my support polygon. When the center of pressure hits the edge of my support polygon, then there's a chance that I'm tipping, okay? If my center of pressure is even a little bit inside the support polygon, then I cannot be tipping. Because in order for my center of pressure to be inside this support polygon, that means I have to have had as much force happening on this side to balance something and pull it into the inside, so I cannot be tipping around my foot. That's been used in the past as saying you cannot be falling down. Okay? I mean, you could still fall down directly into the ground, but people say cannot fall down if your center of pressure is inside your support polygon. That means what they really mean is you can't tip over the side. Okay, so one of the things that people do as a stability heuristic, I would say, really, is they say that the distance of your center of pressure to the closest point of the support polygon, you can use that as a measure of how stable you are. As that distance goes to 0, you're in danger of tipping over. Okay, if you're more in the center, you're good. Okay. So this observation of the ability to sort of separate out the complexity of your humanoid, and decompose it into the center of mass dynamics, so the centroidal dynamics more generally, and then all the kinematics and everything like this, led to a really nice, really powerful pipeline for ZMP-based planning, which is what you saw Asimov doing as it was walking around and avoiding pedestrians. Okay. And it generalizes to more than this, but I'll give you the basic recipe. Okay. It basically breaks things down into 3 steps. First, you plan footsteps. Often using some simple heuristic. Just like I want to stay close to my center of mass or something like this, but it doesn't take into account all the joint angles and everything like that because you don't know what they are. You just basically say, I don't want to move my feet too far apart. I want to move them forward towards my goal, things like this. Given the footsteps, you plan a center of mass trajectory, center of pressure, and center of mass trajectory. And then you can plan joint angles from that. And then online, you do a whole body controller to stabilize. So there's lots of interesting ways that people have done footstep planning over the years. Let me just show you that pipeline in action on our Atlas robot. You'll see as it walks up to some terrain or something, it first looks at the terrain. There's a perception step I'm ignoring today. Okay, it looks at the terrain. It tries to perceive roughly where steppable regions. Okay, and then it does a footstep plan first. Whoop, it puts down some footsteps. Okay, that one was a particularly simple one, and this was during the actual live competition, so we were pretty conservative choosing our small footsteps. You'll see it again here. It looks at the terrain again, segments, puts down some footsteps, now constrained to live inside the steppable regions, which is an interesting optimization problem by itself. I guess I cut the video too soon, sorry. Imagine it walked beautifully over the rough terrain. Okay, after you plan some footsteps, here's maybe a better one that has some nominal footsteps. You can get arbitrarily complicated. So one of the games we've played is trying to put more and more of these constraints up into the footstep planner, so you can plan these more complicated trajectories. That was a real problem. Atlas was a little too big for doors. Have you guys ever seen Hans and Franz on Saturday Night Live? Yeah, okay, that's too bad. That joke was good 10 years ago, but yeah, there's a character on Saturday Night Live that couldn't walk through doors. He was too buff, and he had to walk sideways through the doors because he was too pumped up, worked out too much. Anyways, Atlas was kind of like that, so we actually had to do that for a long time. When they switched the elbows around, we finally could walk through the doors, just barely. But if you swayed too much when you're walking through the doors, then you were gonna, that was a real problem. And Robin, for a long time, was making heuristic footstep planners just to get through the doors. And he's like, I will never do this again. I need to just solve this problem and move on with my life. So he wrote a pretty compelling footstep planner that finally solved that problem. Okay, but that's what you should have in your head for this step, is that somebody's going to lay down a bunch of footsteps. Okay, and since we're talking about center of pressure and center of mass, let's think about how I go from footsteps into center of mass and center of pressure trajectory. Okay, so using my view from above, this is foot 1, foot 2, maybe foot 1 at the next time step, foot 2, something like this, okay. if we think of ourselves as being likely stable, you know, and maybe even having some metric for unexpected disturbances or something, based on having my center of pressure closer to the middle of my foot, then a natural thing to do would be to say, I'm going to start with my center of pressure directly in the middle of the support polygon. So when I'm first standing still, I'm going to go like this. Okay, and then I'm about to lift up my first foot, and I'm going to plan this the same way we gave a mode schedule to make the problem easier before. Here we're giving the footstep schedule to make the planning problem easier here. So I'm going to just say, I'm going to write a simple heuristic plan saying I'd like my 0 moment point to go inside foot 2, somewhere in the middle of foot 2, so I can lift up foot 1 safely. Okay, and then I want to go, I'm going to have a support polygon that looks like this for a little bit. So that gives me the ability to safely move my 0 moment point over into foot 1. Then I could pick up foot 2. Okay, and I'm just going to schedule the center of pressure trajectories. Okay, and that turns out to be a pretty robust thing to schedule. And the timing of this matters, actually. So if I then go to say, so I'm going to say at time 1 I'm going to be here, at time 3 I'm going to be here, at time 5 I'm going to be here, something like that, okay? Yeah?
Is this applicable for one specific style of gate, or can you make it work for shuffling?
Yeah, so I think this is particularly good for a walking gait where you always have one foot on the ground. When Asimo, for instance, started running, and when we've started running, we would consider that small excursions from this otherwise planned trajectory and try to stabilize ourselves back. And the more you put into the trajectory optimization, the more dynamic you can go. For quadrupeds, for instance, you can have multiple gaits that have non-trivial timings that always have a 0 moment point description. So you could be diagonal legs on the ground at the same time. Your 0 moment point should be on the line as you transition to the next thing. Okay. I need one more color of chalk here.
So, one question about
Yeah.
so when you're optimizing this trajectory optimization problem, is it just optimizing the CO2 trajectory, or it's also doing the trajectory of the actual configuration of your robot?
Not configuration of the robot yet. This is just the center of pressure trajectory. And I have to say that in most cases, until Robin started thinking about this, and there were other works around the same time that were trying to put more of the center of pressure, kind of combine more of these layers. But the first thing, the simplest version of this, I'm telling you, someone just gives me my footstep planner. I could just imagine a very simple heuristic for kind of laying them out on the path to the goal. And I will prescribe, I will hand design a ZMP trajectory that just goes near the middle of the foot at a certain timing. Straight lines, piecewise linear interpolation, no optimization. Okay? You can get fancier. But what you do then to get fancier maybe is if you then see, based on the intimate relation between the ZMP and the center of pressure, the center of pressure and the center of mass, you can now solve for the center of mass trajectory, okay? And it won't be exactly over the ZMP. It'll track the ZMP in some interesting way. Okay. This is if I were to plot the center of mass projected down onto the ground. Then these equations allow you to solve for that explicitly. You just integrate out, we have the relationship in terms of accelerations, but if you have the initial center of mass, you can just integrate the equations to figure out what the center of mass needs to do to make the ZMP trajectory happen. And what's interesting, the timing really matters, okay? So if you were to make the thing slow, if you move very slowly, then the accelerations will be small. The difference between the center of pressure and the center of mass will be minimal, and you'll come close to following. Your center of mass will stay largely over your ZMP, and you can be a static walker. If your center of mass projected down into the ground is always inside your support polygon, then you'd call yourself quasi-static or a static walker. That's a lousy way to walk, right? It means you have to go like this, right? That's what they did in the 80s. I mean, the robots did in the 80s, yeah. Right? As you speed it up, this thing will get closer and closer to being a straight line. And what's actually super interesting is that walking fast, for that reason, walking fast is actually often easier than walking slow. Okay, so Atlas, for instance, it was, you could say, if I'm walking kind of slow, you kind of have to throw your hips around. Sorry for all the camera work effort here. Okay, but when you're moving fast, your center of mass is almost completely straight, and you can just, very small deviations of your center of mass can have large effects on your ZMP, and you can stay stable. And it's actually easier to execute something where your center of mass isn't swinging back and forth. So, we found very much that it actually, walking gets easier as you walk faster. Okay, Frank. There's no detailed model of the contact here. But where did it go, right? So the only thing that matters is sort of knowing that I can get forces. So if my ZMP is here, which I can guarantee by executing a center of mass trajectory. This is like, if I just know the positions of my feet and the positions of my center of mass, or my accelerations of my center of mass, I can figure out where my center of pressure is, or I can measure it directly, okay? If I have a desired ZMP trajectory and I'm not in the right place, I can apply slightly different torques to stabilize it, or I can move my center of mass slightly differently. Either, you can choose whether you want to sort of stabilize the ZMP or stabilize the center of mass. But in no place in that pipeline do I actually have to know what the contact forces, the model of the contact forces. I just know that by moving in a certain direction, I'm going to move them to a different place in my foot. It abstracted the details of the contact force out, and it turned it into like a simple feedback regularization problem. So that's why I think one of the reasons this was so successful. Yeah?
How often do like the different, whenever you plan, you do kind of all these things kind of as like a one shot, and then like 5 seconds later you do it again, or are you kind of constantly replanning, and are they at different rates, different levels?
The footstep naturally happens on a once per step. If you want it to be MPC, there's often not a reason to do it more than once per step. The center, these things can all be very much on the fly, like the walking around pedestrians and everything like this. These are all super small, linear MPC kind of problems if you even put some of the richer constraints in them. So this is very much run on the fly, real time. It gets, if you're starting to do, picking your way over terrain, it gets more interesting, but that's at the footstep planning level typically. Yeah. Okay. There's a very nice, so let's say you've got now a center of pressure plan and a center of mass plan, and you're executing and you see that your center of mass is a little bit, or your center of pressure is a little bit off what it wants to be. It turns out that because the relationship between the center of mass and center of pressure, given the assumption of constant on the bottom, is linear, or it's affine because it's got an off term, you can actually stabilize your center of mass trajectory as an LQR problem. Okay, so a natural thing to say, I've got a desired center of mass trajectory. I have a controller, which I can move my center of pressure around to affect my center of mass. Or I could do the opposite. I could say I've got a desired center of pressure trajectory. I'm going to move my center of mass around. In both cases, you have a linear dynamical system that describes that. And you can adjust for feedback. You can write an LQR controller, which you could again solve on the fly, or you could just solve it as an MPC kind of problem. All right, so stabilizing your center of mass trajectory is actually LQR. That's crazy, right? We just talked about compass gates and everything like this. Stabilizing those was much harder. This is not a linearization around some nonlinear system. This is just straight up LQR. The dynamics are actually linear. Time invariant linear. Okay, and then the last part is planning the joint angles. which is actually I guess there's two steps. There's planning and then there's stabilizing in the joint angles, okay? Planning the joint angles is a kinematics problem, and it's, typically we solve that. If you have a 6-link leg, you can solve it in closed form, but we typically solve it with nonlinear optimization, but it's a very simple, robust nonlinear optimization for the kinematics, okay? Because what you'll do is, for instance, given this trajectory and given the timings, which are preordained now at this step, I need to plan something that keeps my center of mass, right, at a certain location over time and moves my foot to to the next location over time. So we tend to make these like little parametric curves that take my foot from here to here. That's my swing leg trajectory. And then once I've got that swing leg trajectory, now I can find the joint angles of all my other parts to make my center of mass follow the desired trajectory. And those are all small kinematics problems to solve. When you're done, though, you can do whole body control to make the whole thing work. I've kind of gone off my script here, so let me see if I... Yeah, so I showed you that. So Scott is who's running the Atlas team at Boston Dynamics. I just wanted to show you that when Scott talks about even his parkour, he shows the same centroidal dynamics models, right? That is what they're using. This is his rendering of a centroidal dynamics model for Atlas, right? Let's assume a spherical cow. I guess he needed, by the time you have angular momentum, it's like becomes an ellipsoid, not a sphere. But that's very much the pipeline that's being used there. And this is what we were doing, the generalization of this where you have both center of mass. So both Atlas and Little Dog relaxed the assumption of a constant height and included angular momentum, but it still used this centroidal dynamics and then just added in the kinematics into the optimization. This is our Atlas running with the same algorithm. Okay, we never got to see the real robot do that, sadly. The one on the top here was just jumping off a step. I'll tell you about that in a second. And we were actually trying to do parkour back in the day because my kids were watching American Ninja Warrior. So I really wanted them to think I was cool. So I don't know, I can't remember if I told you this story, but so I'm a little jealous of the Atlas team at Boston Dynamics because they get to break their robot all the time. When we had the robot, they basically said, if you let the robot fall to the ground and it breaks, we can't promise we'll fix it before the competition. Like, don't take your chances. Stay on belay all the time. It was like we had to be really careful with the robot. So even though we were planning trajectories in simulation of like jumping and stuff like this, we were too afraid to run it on the real robot. Except for the one day where they said, we're going to upgrade your robot. So on, whatever, January 13th or something, we're going to come by and we're going to take your robot back and we'll give it back, 2 weeks. We thought, well, if it's going back anyways. So we ran like one series of dynamic jumping experiments where we're jumping off boxes and stuff like that. We never quite stuck the landing, otherwise I'd show you the video, but that was like we had like a 4-hour window of like productive experiments of our nonlinear optimization on the real robot. But now they're doing it all the time, right? That's what these guys are doing. I'm so jealous. They crushed it. All right. So yeah, please.
What was the biggest issue translating from your successful simulation into putting it on the robot?
Yeah, good. So there's a lot of sim to real, if you will, gaps. I think the centroidal dynamics actually abstracts away some of the modeling issues. We didn't get perfect torques at the legs. The actuators, the robot was heavy enough. Our version of it was 400 pounds. And they have these big hydraulic cylinders in the leg, like massive objects. But if you watch them, we actually put a high-speed camera on them. If you watch them, they deform under the weight of the robot when it's doing really dynamic things. Like the links are bending while we're jumping, right? So that didn't help. State estimation is always a big one, right? So So you think you're one place, you're acting like you're another place, whatever. So I think we did a lot more work on state estimation, but I think for the very dynamic things, that was, 1 day of dynamic things wasn't enough to tune up our state estimator for that regime. Yeah.
So when you're walking and you've got your center of pressure trajectory, like as you go faster, it's kind of speeding up this zigzag.
That's the amazing thing is your center of pressure trajectory, yes, is speeding up, but the center of mass trajectory needs to do less in order to get big center of pressure deviations. So you'll get, as you speed up, this will get closer and closer to a straight line.
I guess my question is, at the limit of running, it becomes like discrete points, right? And then now like your center of mass is one place and your center of pressure is not.
Yep, that's true. So what happens in the running case? So if I lift off, then I guess my center pressure is not defined for a moment, and then I come back. What I want to do is catch it in a place that it would be close enough to my, inside my foot that I can apply any stabilization I need. If you were exactly on plan when you jumped, then you have nothing. You're fine. Okay, but imagine your model was a little bit wrong. You landed a little bit off. Your center of pressure, your center of mass is a little bit off where you expected it to be. Then if your center of pressure was planned to be in the center of the foot, then you'll have enough time to react and sort of get back on track before your next jump. Yeah? Yeah.
Just thinking about dynamic things, even just picking up one foot and putting it back down. The support polygon has timing to it, right?
Yes.
You have 2 feet and then you have 1 foot and then you have 2 feet. Do you have to worry about not going outside the edge of what you do have? Like
Yep.
the planning of the center of pressure is not quite as straightforward as it looks there, right?
You're absolutely right that you have to be careful that the timing of your foot picking up, you wait to pick up your foot until you're inside here. And since I've got my foot sequence ahead of time, but it's really not that hard to write that procedurally. It's not like.
You do it backwards. You optimize this and then you make sure that the feet happen while the center of pressure is somewhere allowable.
I think we've done both. It turns out it's really not that hard to just pick. These are like linear segments, and you just make sure that you're inside your foot by the time this foot comes up. I agree with you. You could take the kinematics of the foot, pick the timings here, and then set the timings of the foot. That would be a nice, simple way to do it too. Maybe wait till you're, not just on the boundary, but a little bit inside here before you lift up your foot. Yeah, that's right. But you're right. There's definitely timing involved in this picture that's not easily on the board.
Can you touch more on the footstep planning and any interesting things that kind of reside in there?
Yeah, good. So the original simple footstep planners were really like, I've got some kind of potentially convex region around, around my current foot position that I would be safely move, and I'm allowed to pick anything in that region, sort of ignoring all the details of my dynamics, of my kinematics, and everything like this, in order to sort of make progress towards my goal. So pick the best point in that region to move forward. Very simple, just thinking about feet moving along. The name of the game has been to try to put more of the center of mass dynamics and even angular momentum dynamics into the footstep planner. And that gets into now you have discrete decisions to make, plus some continuous but linear dynamics. So that actually fits nicely into mixed integer optimization, mixed integer continuous, even convex optimization. So we've had a series of works that tries to write mixed integer optimizations. And I think we're probably going to ask you to look at that for a problem set. And I'll talk a little bit more about the mixed integer formulations when we do planning in the next couple lectures. But I actually think that picture is very important. We've moved the complexity of the nonlinear dynamics into a more explicitly discrete set of decisions with simple continuous dynamics. And this was a mind shift for me over the years, right? I was very interested in nonlinear dynamics. And I think as the problems got harder, ironically, the nonlinear dynamics mattered less. And the discrete decisions about when you make contact, where you make contact, were more important to task success. Certainly for manipulation, that's true. And even for walking, that became true. So I slowly shifted my mindset to thinking about it a bit more like a combinatorial problem and less like a continuous nonlinear optimization. Yeah?
So what happens between Parkour, is every footstep planned out, or is it dynamically determining where it's being planned?
So I don't know every detail, right? I infer things based on, and I know the students that, the people that are doing it, I know some of them well. Yeah, I think they have libraries of trajectories that they're using, and they probably don't do this exactly because they do have big aerial phases. I think they're more in the centroidal dynamics trajectory libraries, and then they find closest trajectories to what they want to execute and stabilize. If I had to guess, I mean, we could flesh that out more, but if I had to guess at a high level, what are they doing? I think they've got libraries of trajectories of the centroidal dynamics. They find the closest one to what they're about to execute, and they do have I suspect they do have a choice of which step they're going to step on in which order and stuff like that. And they pull it from the library, and they talk a lot about online model predictive control. So they're constantly replanning those trajectories from those initial library on the fly. Yeah.
When you've got those like rocking chair feet, does it just become an extra constraint of like now the center of pressure has to travel along the foot length during the time of contact?
So that's a great question. So the passive walkers had these big curved feet, right? And they walked beautifully, right? And Asimo has these big flat feet, and people don't love the way it walked, right? But the math works better for the flat feet case, right? So the curved feet, I think, doesn't jive with this very well. You're going to always have a constraint of a point, and the kinematics of your decision at this level demands this. There's no like there's no room for optimization in here after you've picked the footstep, so there's not a really nice split there. You've seen, so humans don't walk with flat feet like that. So there's been a series of walkers that have tried to make this go farther and farther, like they'll have a big flat toe, right? And then you go up on your toe to sort of look like you're doing this, and you can still do it. But at some point, I think this is, the lessons from this about the planning the contact forces first and your centroidal dynamics being a pretty good approximation, those scale. But the actual ZMP thing is pretty geared into flat foot walking. Yeah. Okay, let me just tell you a little bit about the whole body controller that we and other people tend to do for the last step. Okay, so this was our favorite demonstration of showing, this was the hard part of Atlas getting out of the car, and just how robust the controller was at so we had a nominal trajectory of the center of mass and a swing foot, and you could do a lot to that robot, and it still would be pretty robust, right? That was like at 4 in the morning or something. We were so exhausted, and I was laughing hysterically while I was shooting the video. We were so sleep deprived. But super robust controller. Okay, so how does that happen, right? So we're tracking a center of mass trajectory. We're tracking, let's say, a foot trajectory, and we're making instantaneous decisions about how to move the joints. And it's actually very simple, and it's simple enough that I want you to see it. The basic idea is these are QP, quadratic program, inverse dynamics controllers. That's for quadratic program, yeah? So we know that the equations of motion of our robot take the manipulator equations, even for Atlas, right? I'll even call these force here. Okay, and what's interesting is that the way that the forces enter the multibody equations is this particularly simple form. They come in a control affine, in an affine way. This is a Jacobian that relates it's the gradient of basically the sign distance function that describes those forces, but it's the kinematics of where that force is located, which maps it into the joint torque coordinates. Okay, B might be not full rank, because Atlas is under-actuated if it's got a floating base, right? But all of its internal joints are actuated, but it's just its floating base coordinates are not actuated. Okay, so what we have is a desired center of mass trajectory. Let's say we want to track the center of mass. So let me call that, I've got P center of mass over time. The first thing we do is we make a reference COM trajectory. Which is basically a PD stabilized version of our, let me call this the desired versus the actual. So this one was planned, it doesn't know anything about stabilization, but instantaneously I'm going to look at where I am, and if I'm not exactly on the plan, I'm going to put a little corrective term that kind of pushes me back towards the plan. Right, so that's just enough to say that if I found myself over here, I'm going to make a nice corrective plan that gets me back. And what we do is we solve a small optimization problem at every time step when the robot's running, which doesn't solve the full optimal control. It just solves the instantaneous control that you need to be as close as possible to the reference acceleration. Okay, so we say find me Q double dot U and the forces that minimize the difference between my reference acceleration and my true center of mass acceleration. I could put in other terms here like plus the foot reference trajectory. I'll focus on the center of mass as the main objective right now. And I do that subject to the dynamic constraints. Subject to the torque limits. What's interesting, right, is that so far, in this case, in the online control case, Q and Q dot are given, right? So all of the nonlinear terms in my equations of motion are actually constants. And this is a linear set of equations in my decision variables. These are linear constraints. That's a quadratic objective. Okay. Actually, if it was only this, since if it was only these equality constraints, I could potentially just solve it in closed form. But this U is an inequality constraint, and the other one we do is we say that the force has to be inside the friction cone. That's the biggest reason why we end up with a quadratic program instead of an unconstrained least squares. Okay, so instantaneously, I'm going to choose the Q double dots. These are joint angles, accelerations, such that given the dynamics, my center of mass dynamics is as close as possible to my reference center of mass dynamics. And this is a simple, because in the one-step case, right, this is not looking ahead into the future. In the one-step case, this is a convex optimization. The big reason is because Q and Q dot are given. If I were to look, as soon as I look into the future, and Q dot are going to be the function of my first decisions, and then the nonlinearity creeps in. Okay, but for one step, everything's beautiful and linear. And this runs, at high rates on the real robot, and that's what's doing the balancing control. We were solving this with Gurobi at about 300 hertz. Actually, that's not true. Gurobi we were getting as close to 300 hertz, but then we wrote a customized solver that solved this most of the time, way faster actually. We called it FastQP, and then we said if FastQP just used a bunch of heuristics. It wasn't a complete QP solver, but it took the last solution and tried the same active set constraints. If that worked, it was just solving least squares problems. Then it did a few heuristics to try to find a good answer. And that allowed us to solve at even higher rates, okay? And then we said if our little simple heuristics didn't work, we would fall back to Gurobi. And it got to the point where our control system was so dependent on the performance of these low-level controllers that if our FastQP ever failed and we had to stop and call Gurobi, the delay that resulted from calling Gurobi made the robot often fall down, or you could definitely see it have problems. It would jerk or something because of the QP solver got slow for a second. But as our QP solver got faster, the simple heuristics also worked better. So once we got our control rates up very high, then basically the solution you got on the last time step, if your next time step is very soon, then basically not much can happen. And so your last solution is very close to the next solution, and the simple heuristics work very well. Okay, this is not exactly, we solved out U, and we did a couple things to make it a little faster, but this is basically the QP we were solving on Atlas almost all the time. And all the groups that were working on Atlas at the time sort of started converging to these kind of controllers. These worked. This was definitely one of the lessons of the DARPA challenge, was that these controllers work extremely well. Our QP was solving, it had like 90 decision variables and 30 equality constraints and 112 inequality constraints. I looked it back up and wrote it down, and that was completely compatible with online computation. Okay. So it's amazing that it sort of took this hard, nonlinear, long-term optimization, and by breaking it up into those pieces, we got to something that we could just plan on the fly and stabilize pretty well. Yeah?
Have these major solvers seen significant speed up since then? Like, can you get the QP with Gurobi to solve close to fast QP now?
It's a good question. I don't know. We should try. Yeah? Yeah, I don't know. They don't always have our, the general purpose solvers are trying to solve every problem faster. So sometimes our problems get slower, you never know.
Could you elaborate why you need additional DD controllers?
It's roughly, if you see that if your initial center of mass trajectory was this orange, and you find yourself in a different center of mass location, it's just a way to interpolate the original center of mass trajectory into something that's relevant for your current time. The reason you need to do that is because we're commanding accelerations, right? So if we just naively took the original center of mass trajectory, differentiated twice, and applied that acceleration, then we would do something over here, right? So it's just a little stabilization term to command acceleration level, that's something that will get back to my nominal trajectory. It's not a KP is probably, 1 or something. The diagonal matrix, simple. Yes?
Does this transfer to places where you don't have torque control at your joints? If you have, velocity control or something else?
Okay, so
Abstracted away.
it's a great question. So do you need torque control? This I wrote in terms of torque control, but there was a camp of people saying you must have torque or force control to do walking robots. And then there was all these Asimo-like walkers walking around, often in Japan or Korea, and they weren't using torque control, and they were walking beautifully. And the reason for that is because the lesson from ZMP is that people would say you need force control to control the forces of your foot, right? And that's just wrong. All you need to do is be able to move the position of your center of mass, and you are implicitly controlling the forces at your foot. That's the lesson of ZMP. You can control forces with position-controlled actuators. You don't want to do it at a joint-by-joint level. You're doing it at the center mass level. right? So there are variants of this that work just completely with position control. Good question. Okay, see you next time.